All right, our first talk of the second session is about Pyrosome, and Dustin Jamner is going to tell us about it.
All right, so let me tell you about Pyrosome, which is my framework for modular, extensible, equivalence-preserving compilation. And this is joint work with an undergraduate researcher, Gabriel Kammer, and my advisor, Adam Chlipala. So just for some context, existing verified compilers generally target single stable languages. So CompCert targets C, CoqPL', is a compiler for a subset of SML, and there's a reason for this, which is that these languages have sort of very well-established specifications. And that's because updating and extending verified compilers can be potentially very expensive and require arbitrary reworking in your proofs. And this can be mitigated with good proof engineering, but at the end of the day, we don't really have a lot of formal guarantees about what parts of the compiler and what parts of the proof may have to change when we update it. Additionally, verified compilers' meta-theories are usually specialized to their languages. And so, compatibility between separate verified compilers is, somewhat of an issue. So the goal for Pyrosome is to have a language-agnostic framework for verified compiler extension. And I'll touch on each of these points as I go. The long-term goals are to reduce the burden of compiler verification, specifically with regards to extending and updating compilers. And I hope that this will make compilers feasible for new domains like DSLs that require adding sort of specialized features to existing languages, and for evolving languages with living specifications. Additionally, I hope by having a sort of versatile framework for compilers to enable the development of a reusable library of compiler and language components that should make future developments easier. And sort of with the power of extensibility to support language interoperation and multi-language reasoning. Now, to get into the technical components of Pyrosome a bit, the core theory is that of generalized algebraic theories. But what you need to know is that basically a language is a list of inference rules that can mostly look like this, where we can have rules that introduce a new syntactic form and provide the judgment that describes when that form is well typed. Or we can have equations, since semantics in Pyrosome are defined via axiomatic equivalence. And this is an important factor for our modularity and extensibility, since contextual equivalence really is not a good candidate for extension. And if you want to know more about that, you can ask questions at the end of the talk. Now, I do want to sort of highlight one point, which is that this framework really is language agnostic. I'm writing the standard notation here for sort of simply typed term judgments, but this is just kind of syntactic sugar for the thing on the right, where I'm saying this piece of syntax here belongs to these sort of expressions with this judgmental information, given an object A belonging to the sort of types, and E belonging also to the sort of expressions with its own judgmental information. And these sorts are not primitive to the framework. These are also defined as part of the language specification. And just to point out that you can define other sorts exactly, or elements of other sorts exactly the same way as expressions. To add a type, you just say this is a new piece of syntax in the sort type, given these priors. So as a running example in this talk, I'm going to use our continuation passing compiler for STLC. And this is, I think, largely a standard pass with a couple sort of small modifications to make it fit Pyrosome a little better. CPS compilers often have an additional argument, which is the continuation to call, which is often annotated on the compiler function. But rather than do that so that we can fit the interface here, I have a distinguished variable k that is the free variable that will be filled with the continuation by whatever closing context is responsible for it. In addition, I'm using a negation type here as a type of continuations in the target. And as many people may be familiar with, negation is just implies false. So that just means a function that doesn't return. And so the interpretation of the function type in the target is just a continuation that takes in the compilation of A and a B continuation to call at the end. And because I'm going to be using it for a couple examples, I'm just going to also step through the rule for lambda. Since lambdas are values, we have to call the continuation and pass it something. And the thing we're going to pass it is a target language continuation that sort of adheres to its type and takes in an argument matching the original one and a continuation, k prime. And then this is sort of how we fill that k. We're just going to compile the body and substitute k prime for k. So we have a compiler. What are we going to prove about it? The sort of signature facts that Pyrosome supports proving at the moment are type and equivalence preservation. And so these have very pleasant characteristics to work with. For example, if we have two source programs, E1 and E2, that are equivalent, and we say that for some compiler F of E1 is equal to E2. And also, if we have another compiler G, whose source is the target of F, we can compose them. And equivalence preservation is vertically composable. Very good. But also, we're in an axiomatic semantics. So these equivalences are all defined on open terms. So as we compose the compilers, this is all in the context of some open terms, which means that we can do linking. And specifically, let's say we have now F and G with different source languages but the same target. And we have programs E1 and S1 and E2 and S2. But E1, I want to point out here, I'm giving one free variable. What I can say is that if in the target language, the interpretation of this free variable's type B lines up with the output interpretation of E2, the type A2, then I can just do substitution to link and plug the program from one compiler into the output of the other. And so equivalence preservation really supports a lot of composition and linking properties. Now, the last thing about equivalence preservation I want to convince you is that it's a sufficient property to really characterize compiler correctness. And specifically, I'm going to look at cross-language relations, which is another common way of sort of defining what it means for a compiler to be correct. So let's say I have some source language with Boolean values and a natural value target language. I might define a cross-language relation by saying that true is related to 1, false is related to 0. And for a source program E, it's related to a target program E prime when they both evaluate to related values. Right? This is sort of a common way of doing things. And I'm just going to adjust it slightly for our axiomatic semantics. So I'm going to say that E will be source language equal to B, and E prime source language equal to N, or target language equal to N. In this case, we could use equivalence preservation on our source equality to say that F of V is equal to F of B. And in fact, what that will give us is that if we can show that F of true is 1 and F of false is 0, equivalence preservation will give us that a compiler F actually satisfies this cross-language relation. And so in this way, equivalence preservation isn't exactly the same thing, but it's kind of the hard part of proving these correctness facts. So now I'm going to, we've talked about why this is the right property. Let's talk about sort of how to prove it, since I've been claiming that the goal is to make the proof easier. And I'm returning here to the CPS compiler that I'm going to use as an example. So typically, we can prove equivalence preservation by induction over the equivalence judgment. If we have E1 equals E2, we want to prove that the compiled versions of E1 and E2 are related, then we can look at the derivation of our hypothesis and have one case for each axiom that we could be using. So I'm just showing one of the cases here. This is the case for beta reduction. We're going to have the compiled version of an application of a lambda, and then the compiled version of a substitution, and we have to show that those are equal in the target. So in this sort of elided portion here, there's going to be some reasoning pushing the compiler in and evaluating how it processes the term, and then some equational reasoning. And eventually, we're going to get down, and we need to show that the E1 on the left is equal to the E2 on the right once they're compiled, and same for E1 and E2 prime. And so then we can use induction and tie back to the start, and we have our proof. So I've sort of gone through how we set up each component of defining a compiler and proving it correct. Now I'm going to talk about how we extend all of that. And for the example in this talk, I'm going to use a fixed point operator, a recursive function definition that behaves similarly to lambda, except that the body E also has a free variable representing the recursive calls. And we can sort of define how to extend the compiler intuitively. This is just intuition right now, by adding another case to our compiler rules that says, well, we could also have the syntax for a fixed operation. And so we'll compile that largely the same way we compile lambdas, really. But the important part is that we're just adding one more case. And so to look at this from a bit of a higher level, we start with STLC, and we use our CPS transformation to compile it into a continuation calculus. Actually, there's one more point I want to mention. Notice there's a fix on the right here. And that's because the sort of features that are in the base continuation calculus are all terminating. So we need to extend both the source and the target to adequately support this feature. And so that's what we're going to do here. We have our CPS compiler, and then we need to first add a feature to the target language. And this already requires some thought to make sure it's OK, since we've changed the target language of this compiler. So is it still correct? Well, in Pyrosome, we have a monotonicity theorem that says that all of our judgments, equivalence, well-formedness, are sort of preserved under language extension. And so what we can do is just embed all of our terms from the cont language into the cont plus fixed language. And so the correctness properties of the compiler still hold, and everything's great. Then, to extend the source language, we'll add the features I've been talking about informally. We add the new syntax for fix. It also needs a beta reduction rule that I haven't shown. And then the compiler needs exactly one case, which is the case for compiling the new syntax. Now, to extend the proof, it actually looked very similar. Since we have one new piece of syntax, the type preservation proof, not shown, will have one new case. And since we have one new reduction, beta reduction for fix, the equivalence preservation proof will have a new case that looks very similar to the beta reduction for lambda. And so likewise, we'll just be compiling the term, doing some equational reasoning, and then appealing to induction for the sort of meta-variable subterms. And so the great thing is that in Pyrosome, we capture this informal idea in an inductive predicate here. So finally, we have some Galena code. And the way this predicate works is it's defined on the compiler as a list of match cases, and the language as a list of rules. And the base case here, the empty compiler compiles the empty language, no problem. And then the next case here is the case for when we add a new piece of term syntax. So if we add a new term rule, this could be the rule for application, the rule for lambda, the rule for the arrow type, just a new piece of syntax. We have to tell the compiler how to translate that piece of syntax and give the compiler a new case of the match. And now our proof obligation is that the E, that's the sort of codomain of the compiler, needs to be a well-formed term in the target language. And the same thing kind of happens for equivalences, where when we add a new equivalence rule to the compiler, we don't need to, to the language, we don't need to extend the compiler because there's no new syntax being added. But what we need to do is prove a new obligation that says that the left and right-hand sides of this axiom are equivalent when compiled into the target. And the great thing is that with this inductive defined, we prove as a theorem that this inductive implies both type and equivalence preservation. So you can do your proofs by proving this inductive and then use our theorem to get the properties you expect. And this is actually very powerful because firstly, it means that it sort of gives you a formal way to specify the informal formula I was talking about with one case per constructor, one case per axiom. And secondly, it means that once you've proven this preserving predicate for some compiler, you can add new rules to the source language and extend the compiler just by using the cases of the inductive that I showed. And to give you an idea of sort of what we've developed so far, this is a sort of example from our ongoing case study. We have STLC and the fix operation, as I've mentioned. We have a subsequent composed closure conversion passed for them as well. We also add references in a heap. and do closure conversion for that. And all of these behave in the same way, where you have to extend each language as you go to support the features that you're trying to compile. But to point out that we can also do things a little differently, we can add a let feature to the source language that just compiles away when you get to the continuation passing language. And none of the compilers on the right-hand side, actually none of the other compilers at all have to know about it. And it doesn't affect the target language at all. So for the rest of the talk, I'm going to sort of go into some of the engineering and technical components of Pyrosome, and sort of why it's interesting from a interactive theorem proving developing perspective. So one important point is that we distinguish between metavariables and object variables. And metavariables are the responsibility of the framework, and object variables are the responsibility of the language designers, languages embedded in the system. So actually, all of our object variables are defined by a substitution calculus that is just a regular language in Pyrosome. And all the languages I've been showing so far are extensions of that one. And that's where the expression sorts and the type sort all come from. And so if you look at this judgment rule, this is one of the rules from the expression language. And all of these things below the line here are metavariables. So these are the responsibility of the framework to handle. And they're bound by the judgments above the line. On the other hand, we use the Brown indices for the object variables. And the 0 here, as far as the framework is concerned, is just another piece of syntax. But the object language rules are what gives it the meaning that it references this V, which is the head of the substitution I'm applying to it. And so it's the object language responsibility to define how their variables work. And this actually gives us some real power in terms of automation and mechanization, because we have all the object language variables and such being defined by our deeply embedded rules. And so they're already reified, and we can kind of operate on them. And actually, we have a Galena script that when you define an extension of the substitution calculus, like lambdas or products or fixed or something else, it operates over the rules of that extension and generates all the characteristic equations for substitution. So, for example, when we pass it the sort of defining rule for lambdas, it'll generate this equation below that talks about what happens when you push a substitution under the lambda constructor. And I want you to notice that it correctly identifies that you have to extend the substitution to avoid capturing the argument of the lambda. And it does so by reading the type of the body in the context of the body. Another kind of automation that we support is sort of generic automation for proving equivalence goals. And this automation here is entirely language agnostic. It just takes the rules that you feed it in. It doesn't know anything a priori about the specific language you're working with, no substitution calculus or anything. And the way it works is that it just looks at your equations, treats them as left to right rewrite rules, and tries to rewrite everywhere in your term. And actually, most of our case study compilers are proven fully automatically, primarily using this tactic to solve the hard goals. So to give you a little bit more of a concrete explanation of how that works, if we have the rule for beta reduction, the automation will look at the term, look at this rule, and search for instances of applications of a lambda, and then replace them with the substitution. Now, to explain how this works, I have to take one detour, which is into a sort of proof format that we use. The equivalence of terms and well-typedness judgments are all regular Galena inductives, but those are kind of inconvenient to manipulate and generate directly. So instead, I define a special type of proof of equivalence as an extension of our term syntax. And the way it works is that all the term constructors are congruence rules, and then we can use the names of equations as additional constructors where their meaning is that equation with the subterm substituted into it. So for example, if we have the identity function, this is a proof that the identity function is equal to itself, because we have congruence for lambda and then congruence for x. On the other hand, if we have beta reduction for lambda as our sort of proof constructor with the subterms x and true, then that's a proof that a lambda x applied to true is equal to the appropriate substitution. And since our substitution calculus is in the framework as an object language, we have explicit substitutions. So we have to use a second rule to evaluate that to true, but then we can just compose them with transitivity. And so with this proof format available, the way that our tactic works is as follows. We have the proof state with some goal that we have to show E1 is equal to E2. We feed each of E1 and E2 into an unverified evaluator that takes both of them and attempts to run them, run as many rules as it can on them. And it generates a proof that witnesses the reduction for each one. And then we have a verified proof checker that we can use to sort of process these proofs by applying the verification theorem for the checker, with the proof under question being the reduction for E1 and then the symmetric reduction for E2. And as long as they reduce to the same term, this will solve the goal. We also have a variant of this tactic that leaves the equation between E1 prime and E2 prime for the user to finish. Now, there's a lot of sort of ongoing and future work that I have envisioned for this project. So the compilers, as I've described, are right now just sort of folds over syntax, which I know is fairly limiting, but figuring out that part I think was the hardest part. And so, in the future, I do intend to extend the language of compilers to be much more expressive and capture more more things you might want to actually write. I also have ongoing work to improve the equivalence automation using sort of egraph libraries and features. The tactics I showed just now are very effective for beta reduction, but they don't handle eta so well. And so my hope is that by using sort of existing techniques for proving equivalences, I can get an even more generic tool that will apply to any language defined in the framework. I'm also working on more case studies, such as polymorphic calculi and dependent calculi. And the theory can handle everything fine. The challenge here is just building up the automation and tooling support to effectively implement these calculi in a very generic framework. And lastly, I intend to connect this to existing formalisms, so that way, how I hope things to end up is that I'll be able to do equivalence reasoning about my source programs in Pyrosome using pleasant axiomatic semantics, compile it down, and at the very bottom, translate it out to something like Bedrock or other sort of independent formalisms, so that the end result you get doesn't have to be in terms of the Pyrosome axioms. So thanks for listening to the presentation. Feel free to ask questions or reach out later, whatever you prefer.
Questions?
So about 20 years ago or so, people were quite interested in rule formats for defining languages, and so Peter and other presentations operations wanting. So Peter Moss had a particular formalism to allow such language extensions, and GSOS rule format was mentioned, I think, yesterday in a talk for concurrency. So do you know how your framework relates to these kinds of formalisms, or have you looked at
so the sort of core theory side of it is generalized algebraic theories, which I think the biggest difference between, if I understood what you were saying correctly, and that is that sounded operational, whereas this is axiomatic equations. Yeah, the theory side of things, I'm primarily using for the language definitions other existing theories. So it would be whatever I assume those correspondences have probably already been studied. For the compiler side of things, I'm not as familiar with the work you're talking about.
Hi, Max New, University of Michigan. So if I understand the idea correctly, you're using axiomatic semantics in the source and the target, and so it's easy to verify because you just do it by induction over the source. Yep. So it seems like you've developed a nice framework for basically defining these systems using generalized algebraic theories.
Yep.
But there's other proofs that I would want to do about my system with axiomatic semantics, like soundness theorems and adequacy, right? Denotational semantics. Could you get some of the same benefits modularity there for defining things that aren't translations to another axiomatic theory, but to an arbitrary semantics?
So in the actual mechanization, the preserving predicate that I have and all the compiler proofs, all the proofs around it are actually generalized a little bit from syntax to syntax translations to syntax to model translations, where the model just has to have all of the appropriate substitution properties, basically. And so as long as you can instantiate that model definition, you should be able to use this. But the tactics won't work as well, since the tactics are for proving syntactic properties right now.
Okay, great, thanks.
I'm William Bowman from University of British Columbia. So I think you mentioned linking, and I was wondering if you could characterize what exactly the compiler correctness theorem that you're getting out. Like, is it? It's surely not just for whole programs, but for linking, is it for you can link separately compiled components or anything in the target language?
Yeah. So because we're dealing with open programs, and I was a little bit loose with this. We're not only dealing with open programs, but meta open programs, so programs with open meta variables. The linking results that you get is that anything that satisfies the correct interface at the target language can be composed using target language meta substitution. So if you have, for example, let's say call by name, call by value calculi, right? That you're both compiling into call by push value or some subsuming paradigm, then you just have to write whatever, you can write whatever glue code or bridge code you need to mediate between the output types of those two things. And as long as the types line up in the target language, you can link it.
Okay, thanks.
Hi, I'm Sky from University of Chicago. And when you mentioned adding things like let to your language, you mentioned that further languages don't need to know that let is in the language. Does it work the other way around? For example, can you come up with a generic let statement that could be added to not just CPS, but maybe ANF and other source languages without let knowing anything about those languages, or is it a little bit more interconnected?
So the way extension works is that you can think of your language as a sort of DAG of components that describes the dependency hierarchy of the components. And so the let example I have here depends on the substitution calculus and the expressions that return values. So this let wouldn't be able to fit quite into the continuation passing calculus, I think. Maybe it would. No, it would not quite fit into the continuation passing calculus because the let has a return type and the continuations don't. That said, given that everything is kind of these reified rules, something I intend to look into is transformations on languages that can, for example, move the let down a layer, up a layer. I haven't done this yet, so we'll see if it works, but there are interesting places to explore there.
Could you perhaps say a little bit about the limitations? So in particular, if I want to verify, let's say, I want to redo ComSort or even bigger, let's say like GCC, what kind of optimizations of ComSort do you think you could verify, and what kind of optimizations do you think you cannot verify?
So right now, I do not have adequate machinery to verify any interesting optimizations. This is the framework sort of in development right now, as is. I think that there are absolutely avenues available towards working towards powerful optimizations. So specifically, one thing I want to note is that I have to use equivalence preservation, which is a great property, but somewhat constraining on the compilers to handle cross-language translations. But if you're doing an intra-language pass, then all you have to do is prove that the compiler, let's say, the optimization O, is equal to its input. And this is sort of a more flexible property that I think should allow for some greater design, and composes just fine with equivalence preservation since everything's up to equivalence anyway. Additionally, I think there's some amount of existing work. Here's a citation that I personally, am interested in trying to apply to my system at some point, where sort of rewrite rule-based optimization systems I think are very compatible with this extensible design strategy.
Okay, we should stop there and move on to the next speaker. Let's thank Dustin.